So we have question number 26. Okay, what does it say? Read it well together. A copper block is hung over a beaker of water by a spring balance as shown in the figure. Consider the following positions while the beaker of water is slowly raised upwards. Very easy question, practical one. Position 1, the block is partially submerged. Position 2, the block is completely submerged. Position 3, the block is on the bottom of the beaker. Right. Then the buoyant forces and the readings of the balance with respect to positions 1, 2 and 3 are given by B1, B2, B3 and W1, W2, W3. Which of the following is correct? Extremely easy question. Okay. So suppose this before immersing this in water is the weight. So you have the tension and you have the weight. So tension is equal to what? Weight. Because there is negligible upthrust from the atmosphere, right? So tension should be equal to what? The weight, right? But the moment you sink a bit, when you submerge a bit, right? Suppose you submerge a bit, what's going to happen? Upthrust is acting, right? Upthrust is acting upwards. You know that upthrust is equal to what? B rho G. The volume that's sunk times the density of the surrounding fluid times gravity G, right? The higher the volume that's sunk, higher the upthrust. Higher the volume sunk, higher the upthrust. Then obviously, just look at this, right? So they're giving, what they mean by buoyant forces is the upthrust. Initially, right, at position 1, the block is partially submerged, right? So partially submerged is position 1. So what is position 2? Position 2 is completely submerged. And what's position 3? At the bottom of the surface of the beaker, like this. The volume sunk here and the volume sunk here at positions 2 and 3 are the same. Exactly. The volume sunk at positions 2 and 3 are the same, right? You can understand that. Why? Because the volume exposed to the liquid is the same. But if you consider position 1, only part of the object is sunk. And I said, higher the volume that's sunk, higher the upthrust. Then obviously, the buoyant force 2 should be equal to buoyant force 3, and that should be greater than what? Buoyant force 1. Now you can understand this. So this is the conclusion that we get. Very easy. What about apparent weight? So readings of the balance, right? That gives you the apparent weight, what appears to be the weight. Now you know the moment you submerge. Now look at this diagram again, right? Here I have the tension upwards, I have the weight downwards, mg, and upthrust is there like this. So the tension, the reading is the tension, right? So tension is equal to what? Mg minus u. Higher the upthrust, lower the reading because mg is a constant. Higher the upthrust, lower the reading because weight is the constant. Apparent weight changes, weight doesn't change. I hope it's clear, right? So what can you say? Then, this is what happens. Right, okay? Observe carefully again, but there's one factor to consider here though. The highest weight is in position 1. Why? Because at position 1, I have what? Well, think about it. Is the highest weight in position 1? Think about it. Yeah, highest weight is in position 1 because the upthrust is going to be the lowest. But what about the weight in position 3? Tension is going to be 0 because it's at the bottom. You have this experience, right? So the object is touching the bottom. When it's touching the bottom, tension goes to 0. It's loose. The string is loose. Then the tension is going to be the lowest. If the tension is going to be the lowest, reading is the lowest at position 3. So W3 should be the lowest, right, in value. After W1, who should be higher? Yeah? So W2 is greater than what? W3. But W1 is greater than W2. Why is W1 greater than W2? Because compare W1 and W2. In position 1, which gives you the reading W1, upthrust is lower. When upthrust is lower, tension is higher. If the tension is higher, the reading is higher. So now you understood that, I guess, right? Yeah. Okay, I'm right. So 27th one. The cross-sectional area of a uniform cylindrical metal rod is gradually reduced in part BC to form an object as shown in the figure. The object is perfectly lagged, and the two ends of the object are maintained at temperature of 100 degrees and 20 degrees. At steady state, the variation of temperature theta along the axis L of the object is best represented by. Okay, very easy. Okay, if you consider a lagged rod like this, Okay, suppose temperature at this end is theta 1, temperature at this end is theta 2, and the length of this segment is going to be L. Right. Then the rate of conduction of heat Q dot is equal to what? Conductivity K, heat conductivity K, times the cross-sectional area A, times the temperature difference theta 1 minus theta 2, divided by the length of the rod through which heat passes. Right. So if I draw a graph of the variation of temperature versus length, right, the gradient of the graph is going to be what? Yeah, Q dot times Q dot divided by what? K A is going to be the gradient, because I'm going to take the temperature versus the length. So length goes here now. So the temperature difference is here. So I relate the temperature difference to the length. Then only I can plot this graph. Yes, and intercept also. Right? So then the gradient is going to be what? Q dot divided by K is going to be the gradient. Then the gradient is going to be higher if the rate of conduction of heat is higher. If the value of K is lower, what's going to happen? The gradient is going to be higher. If the area is going to be lower, the gradient is going to be higher. So that's the conclusion, right? Now let's see the question. I had to draw the diagram again. Give me some time for it. Right, so you can fast forward the video if you really want to, right? Okay. So look at this. Right. Okay. Right. So this lagged. It's a very important thing that it's lagged. Right. The temperature at this end is going to be 100 degrees Celsius. The temperature at this end is going to be 20 degrees Celsius. And this is the line that I'm considering. And the length is taken along this line. Right. Okay, so I have points like what? A, then I come to B, then I come to C, then eventually I come to D. Right. What can you see? Right? And L. Alright. Observe this carefully. Now think about the gradients. Okay. The cross-sectional area here is greater than the cross-sectional area here. And the cross-sectional area here is greater than cross-sectional area here. So can you see cross-sectional area is decreasing? That means the gradient should be increasing with time. But in the region AB, gradient should be constant. So I'll have a gradient like this. Temperature is decreasing in this direction, right? Heat passes in this direction, and temperature is decreasing along this direction, and it's decreasing at a constant rate. The temperature gradient is constant. Okay. Then, what about region BC? Okay, what about region BC? Can you see area is decreasing? If the area is decreasing, the gradient should keep on increasing. How can the gradient keep on increasing like this? The gradient is decreasing like this, but the gradient is increasing like this. It's like, you can remember it like you're going to die down the slope, right? That's how I remember children. You're going to die, right? The slope keeps on increasing, right? So difficulty keeps on increasing. So slope keeps on increasing. So then the slope should keep on increasing like this, right? And then, can you see now, if the line is like this for this one, it should be steeper than this. For what? Segment CD, because segment CD has a lower area compared to what? Segment AB. So segment CD should have a lower area compared to segment CD. Then what can you say? Should be graph like this. Constant gradient, but going like this, right? Okay. So it should be steeper. So it's a graph. The answer is the fourth one. This is because the area is lower. Gradient is higher. Okay. Yeah, I think you understood this. Now we have to do question number 28. Yeah, 28. Right. 3 small conducting spheres carrying charges plus Q, minus Q, plus Q are located at the vertices of an equilateral triangle ABC, situated on a frictionless horizontal surface as shown in the figure. Spheres at B and C are fixed and the sphere at A is free to move, right? The possible path of the sphere at A is represented by. Okay, so what are they asking? The possible path of A is represented by what's going to happen to A. So we have to think about the forces, right? Let's concentrate. It's a beautiful question. Just enjoy doing physics, right? Don't be discouraged. Just keep on enjoying subject. Right. Just love something, it will occur to you, right? Just like you love reading music, just like you love reading books, like playing music, like listening to music, just love doing physics. It will come to you. Bury yourself in your table, like arrange your table beautifully, right? Keep the things that you love, right? You can keep some music surrounding you, right? Some background music, and arrange your table nicely and get into this beautiful feeling of studying. And things will start to work. Make it beautiful, make it interesting. Just don't say, well, I've got to pass this exam, I hate it. Not like that. Love and do whatever you're doing, because you've got to live and die. Right. Look at the 20th question. So, what can I say? Okay. So I have plus Q here, right? At B, I have minus Q. At C, I have plus Q. Alright? So this is at position A. So plus Q is obviously, what is plus Q going to do? Is plus Q going to attract or not? Yeah, plus Q is going to what? Repulse. The positive charges repulse each other. So it's repulsion from plus Q. So minus Q is going to attract, obviously. But can you see these two forces are equal? Right? These two forces are equal because the same distance. But what happens is, suppose now, because of this is an instantaneous force, right? It depends on the position. At this position, the two forces are equal and the resultant is going like this. Right? Resultant is going like this. But that is not the path, because things start to change. Why are things starting to change? Suppose this is in this position, because of this force, suppose it came here a bit, because of this resultant force, suppose the plus Q charge came here a bit. Then it's a different story. I have minus Q here and what? Plus Q here. Now can you see this plus Q charge is closer to minus Q, right? It's closer to what? Minus Q. And it's getting farther away from what? Plus Q. So plus Q feels a lower repulsion and a higher attraction, which means it should be bending towards the minus Q side. Do you understand that? So the path should be like this. So the path should be C. Because now when it's getting to this side, when it's shying away from this position, when it's coming to this position, it experiences a lower repulsion and a greater attraction. And it should be going towards this side, towards minus Q in the path.